If you want to use a wide bandgap semiconductor in your next power design, you can't simply take out your traditional silicon transistor and plop in a silicon carbide transistor. You have to have a SiC-specific design for powering them and driving the gate, switching the transistor on and off. So in today's Tech Chat, sponsored by Mouser Electronics, I'm joined by Karsten Düchting, the Senior Manager at Allegro Microsystems, to dig into silicon carbide gate drivers and supply technology. Karsten, thanks for being here. I'm excited for this.
Thanks for having me.
So can you talk to me about where silicon carbide is showing up and how engineers are starting to implement this it seems like in a bit of everything?
Yeah, that's actually a very good observation. Right now, silicon carbide has been around for a while, right? So we've been talking about silicon carbide, gallium nitride, wide bandgap semiconductors for at least a decade now. A lot of the industry leaders, they already converted to silicon carbide. Some are right now in the process of doing it, and others are going from silicon-based MOSFETs or IGBTs to silicon carbide or gallium nitride in the near future. And all of that is driven by a desire for smaller systems, for more efficient systems that are needed in today's industry, but also in today's society, I would say, through an increasing energy consumption, right? We see that through AI, which requires data centers that consume massive energy, but also we see in the streets where the combustion engines are slowly but steadily dying and electric vehicles are taking over there. It goes through the whole range of industries to solar inverters, energy storage, everywhere there where big energy is needed, silicon carbide is on the verge, really.
And I'm blown away every time when I see a chart like this. You know, traditionally you think of power switching and rectifiers and that sort of thing as kind of either high power and super low speed or higher speed but really low power. But with silicon carbide, we're seeing huge power being switched at, I would say, unprecedented frequencies. Can you talk a little bit about who is using these higher frequencies and why?
Of course, right now, as I try to explain, silicon-based technologies like MOSFETs or IGBTs, they're kind of hitting a wall because they are in the market. They have been in the market for a long time. But if you want to really exploit the technologies that we have, you need to go to silicon carbide-based or gallium nitride-based technologies, which offer either higher higher power consumption, or that offer higher switching speeds. And here we see a range of applications that can work with not only one, but potentially also two or even all three of these technologies, right? An onboard charger, for example, in a car will have used in its first generation silicon-based MOSFETs. Now it is probably going for silicon carbide. In the future, maybe it will be gallium nitride. And what I'm trying to say is that most of these applications that we're listing here, it's not set in stone what technology will be used to drive those motors, those electric vehicles, but also who is responsible for the power conversion here. And the more power we need, and also the higher the frequencies go, silicon-based technologies will not be able to cover that. And that's what we've been seeing over the last years.
The chemistry and the technology and the semiconductor physics of this are super beneficial for us. When it comes to actually implementing them and using them, what do driver systems look like? How do you actually use these in a real design?
Good question, because the first step, as we've been explaining, is, all right, we see that silicon-based technologies are not the way to go anymore. And then a lot of designers, they will look at silicon carbide or gallium nitride-based technologies. However, that is only, as I said, the first step, because it is not only that you need to change from silicon to silicon carbide, but you need a whole drive architecture that corresponds to the technology that you want to use here. And the gate drive architecture really defines the silicon carbide system performance, but especially also the board size. So if we have a look at that picture that you pull up here on the right, then you see it is not only the silicon carbide gate driver, the isolated gate driver that is required for driving SiC systems. You also need a DC-DC transformer, you need a DC-DC, you need all of the peripheral components that are displayed here, which obviously increase your bill of material, they increase your size of the PCB, but they also induce a lot of stress into the system, which leads to not being able to fully utilize your silicon carbide switching performance. So you won't be able to get the highest DVDT if your bias supply is not living up to it. Also, if you have a bias supply that is generated, like here, for example, with a separate DC-DC transformer, your electromagnetic interference that is induced into the system will be huge and will cause you problems that you will, in the end, have to manage with additional filters, additional components anyways, and that is something where we said, okay, we need to find a more suitable solution here in the end.
I am curious about EMI. What are some techniques engineers might use to try to limit that EMI?
EMI is a problem that is caused mostly by high switching frequencies, right? You have your silicon carbide FET there, and then you want to drive it with 100 or 120 volts per nanosecond, and these huge and steep ramps, these are causing, in the end, noise, they're causing ripples, they're causing interference that is induced into the lower voltage system as well. And engineers will try to reduce that by using a very low common mode capacitance. However, if you have a system that requires external power supplies, that requires external transformers, then you only by adding this external power supply add 10 to 30 picofarads of common mode capacitance to your system. And that is a problem that is hard to avoid because no matter how you design your bias supply, if it is with a standard DC to DC chip with a component that you can buy off the shelf, or if you use an auxiliary winding from your main transformer, or if you're using simple bootstrap circuits, all of these add extra common mode capacitance to your system. They add components, and they have some limitations there as well. For example, obviously costs, but then also if you're using simple bootstrap designs, then you cannot make use of the full frequency ranges that silicon carbide or gallium nitride support. You're hitting a wall there at roughly 250 kilohertz. You do not have the full ability to go for 100% duty cycle. So it all comes with a few drawbacks if you are using conventional solutions, as we have on this slide here, for example. If we're now taking a classic example, as we see here with a very standard totem pole PFC that is followed by an LLC circuit with a conventional bias generation, then we see that we have, in this case, 9 separately isolated bias supplies that need to be generated by either bootstraps or auxiliary windings by what we saw on the previous slide here and what we talked about. And that adds not only more size, a larger footprint, but also these dark, bulky transformers will have to be used. You have multiple coupling paths that create more EMI. You have qualification efforts, so there has to be an engineer sitting down to design all of these 9. Obviously, you can replicate some of them, but in general, it is tedious work that consumes a lot of space, a lot of time, and also bill of material, i.e. costs here.
I can only imagine walking up to, one of the designers I've worked with and just be like, hey, can you just add another 9 supplies, add another 9 power rails? That would not be a fun conversation to have for sure.
Yeah, and this is now where I think Power-Thru comes in, because Power-Thru fundamentally simplifies the architecture here. So instead of generating isolated bias supplies off the side, each gate driver will generate its own rails locally here. So we were talking about a centralized approach maybe with bootstraps that is rather simple, going towards a semi-distributed approach with auxiliary windings to a distributed approach for bias supply generation, where really each of the silicon carbide FETs of the gate drivers has their own supply with their own transformer. All of that can be obsoleted. All of that can be made super simple with Allegro Power-Thru, where you need nothing but a 12-volt rail in order to supply all of your silicon carbide FETs there. And that's really the beauty of Power-Thru, where we are not dependent on all of these traditional approaches anymore, but can really create our own bias supply locally where it is needed without any extra routing, really right by the FET itself.
So if it's all on the same 12-volt rail, how much sort of isolation and, you know, crosstalk, for lack of a better term, is there between these different devices?
It is really easy to explain that based on how the technology works. So Power-Thru, in contrast to a conventional approach where you have power transfer on the one rail, right, with your transformer or with your DC-DC and whatever, and then through the gate driver, you traditionally, with capacitive isolation, you have a signal transfer, right? Now, Power-Thru is a different approach where both of these signals, both of these logic and power signals are transferred over one internal isolation barrier that is responsible for both the signal, so the PWM transfer, as well as the power transfer. So our gate drivers, they take the PWM signal with the 12-volt supply and shoot it over the isolation barrier, which can be in a module internally or externally through an external transformer for the chipset, which we are right now releasing. And then after that isolation barrier on the secondary side, there's a demodulator that demodulates the PWM signal, sends it to the pull-up and pull-down pins that are then responsible for providing that signal to the gates of the FETs. And then we have also a floating supply that is responsible for extracting the power of those pulses and therefore generates the floating bias supply. And that makes the system so easy, and that's what customers have been very much liking also for our existing gallium nitride portfolio.
So traditionally, for a system like this, you'd be looking at a pretty good number of discrete components and chips to handle the PWM, handle all the power transformation and conversion. What does this look like with Power-Thru? What are my options when I want to put this on my board?
So with Power-Thru, you have two implementation options. On the one hand, an integrated package, which is like a plug-and-play solution, so to say, for a very fast time to market and simplicity, where you have the primary and the secondary die embedded together with a transformer. So it is really one device that you need to drive your FET, but also that supplies the energy for the bias supply. The other option is a chipset solution, and that is actually what we are right now releasing. So the AHV 85003 and the AHV 85043 is a combination of the primary and the secondary die that, by the way, are exactly the same dies that are right now in the module solution, that are, however, accompanied by an external transformer. So this serves for a very small design because you have the flexibility to place your QFNs that are 4 by 4 millimeters wide only anywhere where you like them, and you can put a very small external transformer in between them. And the further advantage that you have is that you are not bound to the isolation of the big package as we have it on the left side, which is a reinforced isolation package. For the chipset solution, you can really design your gate drive with the isolation that you require. So you do not have to pay for reinforced isolation if you only require basic isolation. And then you can use a basic isolation transformer. And that way, the chipset solution is also a little bit more cost effective, dependent on what your actual system requirements are.
So if you have a good idea of what your isolation and power requirements are, going with the chipset approach and bringing your own transformer is maybe the most cost-effective solution, both and space-effective solution. But if you just need something that you kind of know is going to work and you don't have maybe all the design parameters you need, going for the all-in-one package is maybe the best approach.
You're absolutely right. That is the beauty of these two implementation paths that we offer. while on the one hand you have a one-fits-all solution, so to say. You can really narrow down your requirements for the chipset solution with an external transformer that you come up with yourself, given specifications that we can provide to you. Or we also work with industry partners that where we recommend transformers that are in the market already that go with our chipset easily. And therefore, it is also a very simple task to set up your gate drive with our chipset plus an external transformer. And we offer reinforced isolation transformers. We offer basic isolation transformers as well as functional isolation transformers. And all of those, however, they come with basically the same feature set, right? The same obvious benefits that are fast time to market and PCB space reduction. They lead to a reduced bill of material, but they also can lead to a EMI reduction of up to 20 decibels, which is remarkable when, especially when you go from a silicon-based design to a silicon carbide based design for the first time. This will be one of your main challenges.
That is significant. 20 decibels is that's no joke. So is that why is it that much lower?
Because of the very small commutation paths that we can enable with this bias supply generation that is internally realized, and by not adding an additional external power supply to your designs here.
I love a good reference design. Can you kind of walk me through left to right what this sort of topology looks like?
Yeah, of course. So this is the same design basically as we saw before with the 9 different separately isolated bias supplies, now, however, realized with our Power-Thru solution. And going from left to right here, we see this totem pole PFC as an AC to DC conversion, and then we have the DC to DC with an LLC stage. And here it becomes obvious how easy this design has become. So while you had to design 9 separately isolated bias supplies before, here all you need is a 12-volt rail. So with these green VDDs, that's just really 12 volt. There's no extra routing. You can place your gate drivers right next to your FETs. And this obviously leads to then a better EMI, reduced BOM, high isolation robustness, and fast design cycles as well. And reducing the bill of material obviously is also factoring into robustness in the end. So yeah, we're looking at these green boxes, and the design, however, looks the same. But when we look at the actual components that are being saved in, for example, an onboard charger, which consists of a totem pole PFC plus an LLC, then we can see on this page here that it is up to 70 components that can be removed on your bill of material, which leads to a PCB size reduction of up to 50%. And this is something that we've been working on with industry leaders on automotive OBCs, and this is actual data that we gathered from the use cases that we have there. Similarly, on the right side, you see a data center. Well, you see part of the data center application where you can also remove the DC-DC controller, you can remove the transformer, all of that LDO stuff that you usually would need, and replace it by our Power-Thru solution, by our chipset solution, and get rid of 25 components and reduce the PCB size by 20% here as well. This is also from a real-world example where we helped our customer to really meet their goal of efficiency, of size, and of costs here in the end.
So another concern I hear from people designing data center boards and really anyone these days, they want everything to be as available as possible, and they want to get them on their boards as soon as their designs are ready. Are you locked into a certain type of FET or a certain vendor of FET, or what FETs can I use these with? Could I swap them out if I had a supply chain issue, for example?
Actually, one of our biggest advantages is that our chipset solution, as well as the module solution later on, they're very independent of the FET that they go with. In fact, they enable a multi-sourcing silicon carbide strategy for our customers in the end. And that is because they're variably audible in 15, 18, or 20 volt turn-on voltage and are adjustable through a tiny resistor change on the negative voltage between 0 and -5 volts. So what does that translate to? Let's say you're right now using a silicon carbide FET from Wolfspeed, for example, because you're in the US and you want to have a US supply chain. Now, this FET will turn on with 15 volts on its gate and turn off with -4, -5 volts. If you want to change now in other markets to an Infineon FET, for example, or to whatever other FET, you would probably have to go back into your design, tweak the transformer a little bit, or change components there that are responsible for having a bias supply go from 15 to 18 volts or even to 20 volts. With us, on the same footprint, with the same parts, basically, you can achieve going from 15 to 18 to 20 volts on the positive side, or from 0 to -5 volts on the negative side, without any changes in your design on the same footprint, essentially. And that comes obviously with certain advantages, which are not only the cost flexibility that you have when you negotiate potentially with one of the silicon carbide manufacturers, but you have resilience in your supply chain and you have the option to really regionalize your bill of material. So as you were mentioning right now, geopolitical tensions might have purchasers looking into dual supply chain options. We are an enabler really for that because it is super easy to go from one silicon carbide FET to another without doing any extra work in your design there. And that is something that our customers very much appreciate.
So looking to the future of design and even maybe just in the rest of 2026, is there a point where it stops making sense to design your own supplies for these drivers? And just at what point do we just use a chip for kind of everything?
That's actually one of the discussion points that I have with customers because, to be honest, I wouldn't know why in 5 years or even in 2 years from now anyone should bother designing a bias supply anymore. Why would an engineer sit down and design a flyback if it is so easy to integrate everything into one package or into one tiny solution as we have it here with the chipset solution of Allegro? All of the advantages really speak their own languages, I would say. It is transferable between silicon carbide and gallium nitride, which is a big advantage. You have the bias supply generation right where the FETs are, which is very beneficial for the electromagnetic interference. And you have the availability or the possibility to go from one SiC vendor to another. So really, I don't see that engineers in the future will really sit down and generate bias supplies anymore by themselves. We see a trend in the industry also that it will be more integrated, that this is something that the overall semiconductor industry is going for.
Well, it's definitely an exciting time to be a designer of these sorts of systems. Just the availability of new switching technologies inside of the physics, but also with all the surrounding technology, like drivers like this, it's a really cool time to be in this space.
I agree.
If somebody wanted to play around with this, test it out for their design, do you have dev boards available? I think you maybe even can show us one or two just so we can get a feel for the size of them.
Oh yeah, I mean everything is available on Mouser.com already today. So you could just go ahead on the webpage and order either the samples for your designs to play around with. We do have these demo boards which are single channel devices, and here it really now becomes clear how tiny these designs can be really, right? With a functional isolation transformer in the middle now, this is the chipset solution HV85003/043. Or we also do have half-pitch boards which can be used to easily do some double pulse testing for designers that just want to get a feeling of the technology. So this is something that is orderable as well, and I can only encourage everybody to get on the webpage, order some, and try it out for themselves because it is really something new. It's innovative, and it's a lot of fun to work with.
Awesome. Well, this has been really enlightening, and I'm excited for, I may get one of those and play around with it myself. But Karsten,
Sure.
thanks for being here.
Thanks for having me.
That was Karsten Düchting from Allegro Microsystems. And to find out more about the Power-Thru gate driver chipsets or get an eval board or some samples, go to mouser.com/Allegro or use the link below. I'm Daniel Bogdanoff. Thanks for tuning in to this Tech Chat sponsored by Mouser Electronics. I'll see you next time.